Today we're going to be covering Mohr's circle for plane stress and showing how it can simplify your understanding of plane stress and make it simple to determine maxes and mins of both shear and normal stress. Really, it's nothing more than a geometric description of the equations that we learned last time. So we'll try and point that out. Or circle for plane stress. Okay. So if we look at our transformation equations from last time, we can compute sigma x1 to be equal to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine of 2 theta plus tau x y sine of 2 theta. Call this equation star. It's the first transformation equation for plane stress. The second one is for tau x1 y1, and it's minus sigma x minus sigma y over 2 sine of 2 theta plus tau xy cosine of 2 theta. We'll call this equation 2 star. Okay, now if we define a quantity called sigma average equal to sigma x plus sigma y over 2, and then r, which will eventually stand for radius, equal to sigma x minus sigma y over 2 squared plus tau xy squared. Then, if we take the first equation, star, and square it, take the second equation, double star, and square it, and then add the two equations together, we end up with an equation that can be rearranged to look like this. Sigma x1 minus sigma average squared plus tau x1 y1 squared is equal to r squared. Okay. All right, and now what you should see is that this is the equation of a circle. Equation of a circle. And it's centered at sigma average 0, and r is the radius of the circle. Okay. If we plot that equation, we get what's called Mohr's circle. And the axes are going to be labeled sigma x1 y1 and tau x1 y1. Notice that the direction of tau, this is positive. So downward direction is positive for tau. And our circle now is going to be centered at sigma average 0. It's going to have some radius, big R. And this is going to be our angle. It's going to be 2 times whatever theta is. Okay, so if you want to use the measure something at theta equal to 30 degrees, you actually go to 2 times 30 degrees on this circle. Everything is doubled. And counterclockwise direction is a positive change in angle. Okay, so let's maybe show you how you do this. If I give you a plane stress element, let's say sigma x, sigma y, tau x, y, right? So if I give you this plane stress element, we want to plot the Mohr circle corresponding to this condition. Okay. So step 1 is you draw axes. We're going to draw our axes. Tau x1, y1, sigma x1. Okay. Then we're going to locate the center. Step 2 is locate the center. And that's going to be at sigma average 0. So maybe it's right here. Okay. Then step 3 is let's go ahead and locate the point on Mohr's circle corresponding to the stress condition on the x face here. Okay, so in this case, the x face sigma x1 corresponds to sigma x, and tau x1, y1 is just the given tau xy. And I don't know, maybe it ends up being down here somewhere, for example. Okay. And then, so this is going to be the x face, right, the positive x face. Let's also draw the point corresponding to the positive y face. In this case, sigma x1 is nothing more than sigma y, and tau x1, y1 is negative tau xy. And so, let's say that's over here. Okay, let's call this point A, call this point B. Okay, so this is A, B. Okay, now let's go ahead and connect the dots. Okay, and so we're going to start measuring our angle. If we want to rotate, we're going to rotate from point A. And so point A becomes our theta equal to 0 point. Right, so we're going to measure 2 theta from point A. Okay, it's going to be the origin of the beginning of the rotation is the x face. And so that makes sense that point B on the circle is 180 degrees from point A, which is 90 degrees on the element, which is correct. So now we can draw the circle. And now we can just use right triangle geometry in order to find any other point on the circle. For example, if I wanted to find a point here, right, you can simply draw a right triangle, and all you have to do is determine the lengths of the sides of the triangle, and you can compute that point there. Okay, so let's do an example. All Alright, so let's do a couple of different cases. So the first case is we want to draw Mohr's circle for uniaxial stress, and let's just assume for illustration purposes that sigma x is greater than 0. Okay, and so this means that sigma y equals tau xy equals 0. Let's go ahead and plot that on the circle. Okay, so the first thing we do is we plot the center point of the circle, which is just sigma x plus sigma y equal to 0. So this is going to be sigma x over 2. Then we're going to plot the point on the x face. So the x face corresponds to sigma x 0. So it's here. It's going to be point A. Point B is the y face, which is at 0, 0. And we can draw our circle. So now if you want to know maximum shear stresses, you know that the maximum shear stresses are going to be equal and opposite at these points. And you know that this is nothing more than the radius of the circle. And so tau max is equal to sigma x over 2, and it happens at a theta max equal to 45 degrees, because this here is 2 theta equal to 90 degrees. Okay, so there's uniaxial stress. Let's do another example. Why don't we try biaxial stress? In this case, let's assume sigma x is greater than sigma y is greater than 0. And then because it's biaxial stress, tau xy we know is 0. So now this circle looks very much like the previous circle, except now it's shifted to the right. So there's our circle. And then again, tau max is nothing more than sigma x minus sigma y over 2. And it again occurs at 45 degrees. All right, let's look at pure shear. Okay, so pure shear is sigma x equals sigma y equals 0. And then we'll just assume that tau xy is given and it's positive. Okay, now the center of the circle is sigma average, but in this case, sigma average is just 0, 0. So there's the center of the circle. If you look at the y face, or the x face, point A, is just going to be equal to sigma x, which is 0, tau xy, which is positive, so it's going to be here. So there's point A. Point B is just the negative. So pure stress circle looks like this. And so now if we want to know, for example, sigma max, we know that it is equal to just this distance here, which is nothing more than tau xy, and it happens also at 45 degrees. Okay, so there's pure shear. So that's chapter 3. So we've gone through all the different cases we learned in class. Let's go through a case now that's more generic. Okay, so let's say you're given a plane stress state that looks like this. Where sigma x is equal to 90 megapascals, and sigma y is equal to 20 megapascals. And then what I want to determine is the stress state at theta equal to 30 degrees using a Mohr circle. So let's go ahead and do that. Okay, so first sigma average is just sigma x plus sigma y over 2, which is 55 megapascals. And so I have my circle here. I know that it's at sigma average 0, so it's right here, let's say. Point A is the x face stress condition, which is 90, 0. Point B is the y face condition, which is 20, 0. So there's A, B. You should notice this is biaxial stress. Okay. And the radius of this guy is going to be 35 megapascals. All right, now I want to actually, if I start from point A and I rotate, I want to go what? This should be 2 theta equal to 60 degrees. I want to know the stress state at that point right there. Okay, so now this is nothing more than just geometry. So I need to know the distance from the origin to this point. That's going to give me the normal stress, and then the distance from this point to this point right here gives us this shear stress. Okay, so sigma x1 is nothing more than sigma average plus r cosine of 2 theta. Right? So we go to sigma average, which is the center, and then we want to get the length of this side of the triangle, which is r. This is r. So it's r cosine of theta gives me this length right here. And so that is equal to 72.5 megapascals. And if I want tau x1, y1, it's just minus r sine 2 theta, which is just this distance right here. And so that's equal to minus 30.3 megapascals. Okay, and so if you wanted to draw a properly oriented element, it would be an element like this. Right? It's rotated 30 degrees. This value here, sigma x1, is 72.5. And then this is a negative shear stress, which means it's pointing in this direction, so it's 30.3. And then if you wanted to know the normal stress here, you would evaluate this point. Right? So the taus would be just equal and opposite, and then this would just be whatever that distance is.